Hello, this is Jack Jackson. In this video, we're going to be using a GeoGebra applet to visualize the dot product and cross product of two 3D vectors. So in the previous two sections or videos, we defined the dot product and cross product. We defined them via algebraic formulas and learned how to use those formulas to calculate these products. We also learned how to visualize the geometric meaning of these two types of products of two vectors. And we used GeoGebra applets that I created to investigate these situations. However, those illustrations were restricted to having the two vectors in XY plane, making it easier to see what was going on actually, even though we were thinking them as two 3D vectors, which of course is required for the cross product. In this section, we will be using the following GeoGebra applet. You see the link to it below, that I created to release the restriction that the two vectors are in the XY plane. In this app, the vectors can be any two 3D vectors, and they're graphed in 3 dimensions. The details of the computations of the dot product and cross product are shown. So this gives you if you just focus on that part, it gives you a step-by-step illustration of those computations, and it gives you the graphical illustrations of the geometric meanings. You really want to open this one up and move the display around in order to really see what's going on. So let's just go through a couple of slides here first, and then we'll open it up. So here's some static shots from the applet. Notice that you're going to be able to control the all three components, the x, y, and z components of this blue vector v, which is graphed here and illustrated up here. You can control by the sliders or the input boxes. And the same thing for w, the green vector that's graphed over here, which goes from the origin to point C, and the vector v goes from the origin to point B. And we can see that that is also controlled by sliders or by input boxes. We see the definition and computations for the dot product here, definitions and computation for the cross product here, sort of the algebraic versions, and then in the sort of a geometric version here, and here for the dot product, and over here for the uh, magnitude of the cross product. The cross product is actually illustrated as a vector and graphed, which is right this red vector here. And we have some other boxes that you can click on and off to see various things. So focusing our attention on this part and this part, in the next slide, you can see the actual definition of the dot product. Let's just review real fast. If you can take any n-dimensional vectors and multiply the corresponding components and then add those up. So this works for any two vectors as long as they're the same dimension. In this applet, we're considering 3D vectors only. So here's a 3D vector. Here's a 3D vector. How do we compute the dot product? It's -1 times 3 plus 4 times -1 plus 0 times 2. So that's -3 minus 4 is -7 plus 0 is -7. There's an alternative formula as well that's based on this geometric meaning. It's the norm of v times the norm of w times the cosine of the angle in between. Now the norm of v is actually given by this extended version of the Pythagorean theorem. So it's the square root of -1 squared plus 4 squared plus 0 squared. So that's 1 plus 16 is 17 plus 0 is 17. So this 44.1231 is an approximation of the square root of 17. And the one for w is it's actually the square root of, let's see, 3 squared plus 1 squared plus 2 squared. So it's 9 plus 1 is 10 plus 4 is 14. So this 3.7417 is a decimal approximation of the square root of 14. And the angle in between in radians is here. Notice that is an obtuse angle, bigger than pi over 2 or bigger than 90 degrees. And so that cosine is going to be negative. So when you multiply these two together, you do get a negative number. That number represents the length of the second vector projected onto the first vector. So it's the length, it's called the component of w in the direction of v, is this number here, and the length of that projection and the parallel projection, and multiply these two together. and we get, actually turns out to be exactly a -7, which of course it should be because that's how we computed it up here. On the right hand side, this is also in the applet. If you zoom in on this part of it, you'll see the definition of the cross product. One way to remember it is with this determinant, but it boils down to this particular form. So if V is Vx, Vy, Vz, and W is Wx, Wy, Wz, then here's the formula for the cross product. So in this particular one, V is -140 and W is 3, -12. Here's the cross product. Well, you end up, here's a couple ways to do it. Find the minor for I, eliminate this column and this row, and do the determinant here. 4 times 2 minus 0 times -1. That's 8 minus 0 is 8. And for the J, you eliminate this column and this row, but it's backwards from, it's the opposite of the determinant. So let's do this one first. 0 times 3 minus a -1 times 2. That takes care of the negative by doing it in that order. So that's 0 plus 2. 0 minus a -2, or 0 plus 2 is 2. And then for the k component or z component, eliminate this row and column and do the determinant here. -1 times -1 is 1 plus or minus 4 times 3 is -12. So that's -11. So the cross product is 8 to -11. Another way to see that is, actually the way I like to do it is leave off this first column. So let me fix that. Okay, so the way to do this is start with the second one here, 4, then the second component, 4, then 0, then go back to the first component, and then do the second component again. Do that for the other one, -2, -1, 2, 3, -1. Now you could just go down across this way for positives. So 4 times 2 is 8, comma, 0, comma, 2, 4, 8, 2, 4, 0, 2. No, let me say it again. 4 times 2 is 8, 0 times 3 is 0, -1 times -1 is +1. So that's 8, 0, 1 minus 0, -2, 7. And this gives you, no, not 7. Goodness gracious. 4 times 3 is 12. So this gives you the 8, 0, 1. Those are those. Minus the 0, -2, 12. So it still gives you basically to this point right here. So you can get 8 to -11 that way if you'd rather. There's sort of two different ways to look at it. So there's the vector, okay? And we can also compute the norm of this vector. Of course, one way we could do it is actually compute the cross product, like we just did, and then square each of these, 8 squared plus 2 squared plus 11 squared, and then square root all that, and get the norm of that. But it also turns out the norm of that direct product, of that cross product, is by doing the norm of the v and the w separately, which are approximately these two numbers, same as we had over here. Yeah, same as we had here and here. And this time, instead of multiplying by the cosine of the angle, multiply by the sine of the angle. Now, the sine of the angle is always going to be positive because we're talking about an angle between 0 and pi. And if you multiply these two pieces together, that's the length of the perpendicular component. That is, if you project W onto V, it'll have a parallel component. The shadow will be of this length over here, the absolute value of this, about 1.6977. And then there's be a perpendicular component to that, which will have a length of about 3.3343. Okay, and if you multiply those two together by the original length of V, you'll get, in this case over here, one rectangle area, in this case a different one. This is a dot product over here, -7, and this 13.7477 is the area of a different rectangle. It's also the area of a parallelogram with these two vectors as sides. So that gives you the magnitude. Now the direction of the cross product is always perpendicular to both of the original vectors. And we can kind of see some of that in the picture. If we go on, here's a static picture kind of zoomed in closely showing the area represented by the dot product along with the projections. So it's really kind of hard to see what's going on here in a static picture. We'll look at it in the app here in just a second, but here's one of the vectors and here's the other one. And if we project one on the other, we get a perpendicular and parallel component. This black piece here, if we rotate it around to here, perpendicular to this one, those black links are actually the same. It doesn't necessarily look at it because you're looking at it from an angle. But this is actually supposed to be a rectangle. It is a rectangle. Again, we're looking at it from an angle. But the area of that rectangle is the dot product. Well, that's the absolute value of the dot product. In this case, the dot product's negative because this projection is pointing opposite of this vector here. One of the sides is the original vector here, and the other side, the length is the length of that projection in the same direction, the parallel projection, and the parallel component. And the perpendicular component is the length here. And if we bring that over and make a rectangle, then that area of that rectangle, which is the same as the area of the parallelogram with these two vectors as the sides, actually gives you the magnitude of the cross product. Okay, so that's what that looks like in the slides. Now let's actually look at what's going on here in the video a little, in the program a little bit. So let's get rid of everything first of all except for the two vectors. And so those are the two vectors. Negative 1, 4, 0, that one's actually down in the XY plane, down here, and it should be blue. Let me turn it back blue again. I'm not sure how the color got changed, but it's supposed to be blue. Okay. Okay, so there we have a vector there. Goes from the origin to this point B. Let me, you can actually control the vector by moving the point B as well. See, isn't that cool? See, it changes the, and the point C changes at least the X and Y coordinates of the other one. So we got a couple of vectors here. Let me just experiment with that a little bit. So there we've got a couple of vectors. Now, we can look at the angle between the two vectors. Oh, look at that. I made them a right angle at the moment. Let's make it where it's not a right angle. So there we go. And so you can also see, if you kind of look at it, that those define a plane. There's exactly one plane that contain those two vectors. So just looking at it from different angles, you can kind of see what's going on there. Let's see if I can. Flip this around a little bit. Okay, so there's kind of maybe a more standard view of it. So there we go. Okay. Now we could also look at, let me turn that off. This looks at the projections. So if we take, let's see if I can look at it kind of from a different angle. So if you take this vector and project it, let's see, we want this, we want the W projected on the V, on the V, yeah. So we want to take this, the W right here, project it onto this one. So that gives you a component in the same direction right there, and then a perpendicular component there. Let's make this a little bit bigger. It might be a little bit easier to see the projections if I look at that one there, for example. And let's make this one a little bit. There we go. Now that's a right angle there if we turn it the right way. Yeah, you kind of see what's going on there a little better. Okay, now let's look at, oh, by the way, it actually comes up with what these vectors are. This projection in the same direction is actually called the projection of W in the direction of V. And that's this black vector here called P. And the O, the orthogonal projection, is this purple vector going here. And we can see it as well. There it is. The magnitude of the orthogonal one is here. And the magnitude of the parallel one is here. Okay, let me leave that projection on. Let's look at the dot product. So again, here's how you compute it. Right now I have 2, 7, 4, and 15, negative 2, 2. So just multiply the corresponding components. What do you get? You get 30 minus 14 plus 8 is 24. But we can also see the dot product as a rectangular area here. So what we do for the dot product is we take this, okay, let me hide it a minute. We take this parallel component here, and that's going to be the length of one side, and the other side is going to be the length of this original vector. So if we take that parallel component and sort of rotate it 90 degrees, you get a rectangle, and that rectangle is the dot product in this case, since this is positive. Sometimes the dot product's negative, and then that rectangle is the absolute value of the dot product. So again, look what we got. We got one side is the original vector, the first vector, V, and the second side is the projection of the second vector onto the first one. It is that parallel component times it. Now, if we look at the cross product, there's the actual vector. It's too long. It's sticking out the box because it's kind of long here. It's 124 almost 125 units long. But there it is in its direction. But we can take this and look at the area. It's going to be pretty big in this case. There it is. And again, it's going to have the side here, okay, as one side. But this time the other side's not this parallel part, but the perpendicular part. So this purple vector is the other side there. And so that area there is the area of that makes the cross product. Now we can also visualize that as a parallelogram instead, and the parallelogram is formed by two of the sides being the two vectors. So you can kind of see the plane there that has those. Let me turn off the projection a little bit. So there's the plane. And notice that this you can't see how long it is. It's 100 and it's this long, right? 124.5 approximately. But you also notice that it's perpendicular to both of these vectors, to this plane where this parallelogram is. It's perpendicular to that. And it's given by the right-hand rule. So if you point your fingers in the direction of the original vector here, take your right hand, sort of centered at the origin there, point in the direction of this, and then rotate around towards this one with your right hand, so it's rotating the shortest distance around, then your right thumb will be pointing in this direction right here. So it's given by the right-hand rule. Now, if we took this vector here and divided by its magnitude, we would just get a unit normal vector. We would get a vector that is perpendicular to that plane. It's that one is pretty small in this one right here, but if I kind of zoom in close, you can kind of see it right there. Length 1, that's a unit vector in that direction. Okay. This norm of W times the sine of the angle theta, this 14.9 something, that was the length of this purple projection. And again, multiply that by the length of the original vector, that's the area of that rectangle or that parallelogram, and that's the magnitude. That's also the length of this vector right here. which is the cross product. If you take the norm of W times the cosine of the angle right there, that 2.889 something, that's the length of this this component right here, parallel, or the length of these black sides here for that rectangle that we can do for the dot product. So if you get in here and play around with these inputs and outputs and experiment with some different ones, and then kind of move it around so you can kind of see what it is you're dealing with, then you can get a better feel for this. Any kind of static picture does not do justice to the 3D that's going on here. You kind of need to move it around and see what it looks like from different angles so you can kind of get a good feel for what's going on. Okay. All right, I'm going to save that like it is at the moment. All right, so again, this is a GeoGebra applet. It's also found in my my collection of calculus apps. So you can go to this calculus collection and you see apps for all types of things throughout the calculus sequence. These are down here under vector functions. And some of these I did, some of these other people did. So this one, and this one, this one, this one, this one are mine. Here's one, there's one. This one is right here, the one we just did. And so here's some other ones that we'll be using for later on when we come back to vector functions later on toward the end of the course. All right. There's a good introduction to this app and a kind of review of what we've talked about on 3D dot products and cross products and visualizing now in the full generality in 3 dimensions.